So let's take a look at Taylor and Maclaurin series. Now the formula for Taylor series is going to be the series from n equals 0 to infinity of the nth derivative of f of a, and a is just going to be the center value, times x minus a to the nth power over n factorial. And so the first couple terms using the Taylor series will look something like this, where you have f of a plus f prime of a times x minus a to the first over 1 factorial plus f double prime of a times x minus a squared over 2 factorial, and so forth. And so for the Maclaurin series, remember the only difference between Taylor and Maclaurin is that Maclaurin is centered at 0, so the a value will be 0. So the series of that will be from n equals 0 to infinity of the nth root of f of 0 times x minus 0, which is x, to the n over n factorial. So the first couple terms will look something like f of 0 plus f prime of 0 times x to the first over 1 factorial plus f double prime of 0 times x squared over 2 factorial, and so forth. So for number 1, we have f of x equals e to the x, and our given center value is 3, and we have to find the Taylor series and the radius of convergence. And so since this asks us to find the Taylor series, not the Maclaurin series, we can't use a shortcut, because we know the shortcut of e to the x in the Maclaurin series is a series from n equals 0 to infinity of x to the n over n factorial. So if it asks us to find the Maclaurin series, we would be able to use this shortcut, but it asks us instead to find Taylor, so we can't use that. Instead, we have to use the standard formula. So I'm just going to start by finding the first 4 terms. So if f of x is equal to e to the x, then f of 3, if I plug in the center value, f of a, so f of 3 is going to be e cubed. And notice that even if I take the derivative of e to the x is still e to the x, so I'll continue to get e cubed no matter what value, or no matter what derivative I'm in. So even f double prime of x is still going to be e to the x, and so f double prime of 3 is going to be e cubed. And let's just find one more. So f triple prime of x is still e to the x, and so f triple prime of 3 is still equal to e cubed. So now let's write the Taylor polynomial. So the Taylor polynomial, once again, is going to start with f of 3, or f of a, your center value, and f of 3 is obviously e cubed. So we're going to have e cubed plus f prime of 3, or f prime of a. F prime of 3 is e cubed times x minus the center, and the center is 3, to the first over 1 factorial, plus f double prime of 3, which is e cubed still, times x minus 3 squared over 2 factorial, plus e cubed, which is f triple prime of 3, times x minus 3 to the third over 3 factorial, and so forth. I'm just going to go ahead and write the first 4 terms, like so. So remember, the Taylor series formula is equal to the series from n equals 0 to infinity of the nth root of f of a times x minus a to the nth power over n factorial. And so we have to write a series given this polynomial that looks similar to the Taylor series. So let's just start out with the nth derivative of f of a. Notice how no matter what derivative we were in, whenever we plugged in 3, we always got e cubed. So e cubed is going to be our nth derivative of f of a in the series. So when I write the series, we'll get the series from n equals 0 to infinity of e cubed, which is the nth derivative of f of a. Now for x minus a to the nth power, notice how we have x minus 3 to the first, then x minus 3 squared for the next term, and then cubed for the next term after that. And the reason it's not in the first term is because that's basically x minus 3 to the 0th, which is just 1. So we have to write times x minus the center value, which is 3, to the nth power, over, now for n factorial, when we look at the polynomial, it's basically the first term is e cubed over 0 factorial plus the second term over 1 factorial plus 2 factorial, 3 factorial, and so forth. So that's why we have n factorial in the denominator. And so that is the series of e to the x at the center value of 3. Now you can always double check by plugging in different values of n, different values for n, and see if that matches the polynomial, but you should get the exact same thing. Now in order to find the radius of convergence, in this case it's best to use the ratio test. And before I do that, since e cubed is like a constant, we can actually take that outside the series, similar to in integrals. So I can rewrite this as e cubed times the infinite series from n equals 0 to infinity of x minus 3 to the n over n factorial. So now when I use the ratio test, I'm going to take the limit as n approaches infinity of the absolute value of x minus 3. So now remember, we're going to replace n with n plus 1 over n plus 1 factorial. Now I can either divide by the sequence or multiply by the reciprocal. So we'll multiply by n factorial over x minus 3 to the n. And so to simplify, I can expand the exponent and both the factorial as well. So I'll rewrite it as x minus 3 to the n times x minus 3 to the first times n factorial over, now when I expand n plus 1 factorial, I can rewrite it as n plus 1 times n factorial times x minus 3 to the n power. Now when I do so, the n factorials will cancel, and the x minus 3's to the n's will cancel. So we're left with the limit as n approaches infinity of the absolute value. Now remember, it's probably good to keep the n's and the x's separate. So 1 over n plus 1 times x minus 3. That way it's easier to evaluate the limit. And so when I plug in infinity for n, we'll basically get 1 over infinity, or 0. So we'll get 0 times x minus 3, which is still 0, and the absolute value of 0 is 0. And for the ratio test, remember I have to set it less than 1, because that's where we can find the interval of convergence if it is less than 1. And this is a true statement. 0 is always going to be less than 1, which means the series converges for all values of x. And if it converges for all values of x, that means the radius is infinity. So that is the Taylor series and the radius of convergence. So now for number 2, we have cosine of pi x, and we're trying to find the Maclaurin series and the radius of convergence. So notice how it says Maclaurin series. So now we can use a shortcut here because it's centered at the value of 0. So remember, the cosine, the Maclaurin series for cosine of x, if you memorize the shortcut, is a series from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. And so we're trying to find, we have cosine of x, the series for that, but we're trying to find cosine of pi times x. So notice, instead of x, we have pi times x. So wherever we have x in the series, we're going to replace it with pi times x. And so we get the series from n equals 0 to infinity of negative 1 to the n times, and now remember, we're going to replace x with pi times x, so pi x to the 2n power over 2n factorial. And that is the series, or the Maclaurin series, for cosine of pi x. So when you know the shortcut and it's asking for a Maclaurin series, this will save you a bunch of time. Now in order to find the radius of convergence, we have to use the ratio test once again. So once again, we're going to set the limit as n approaches infinity of the absolute value. Now remember, when we use the absolute value, we can automatically take out the alternator, because that doesn't matter when we use absolute values. So we have pi x. Now in the ratio test, remember, we're going to replace n with n plus 1. So 2 times n plus 1 over 2 times n plus 1 factorial. Now I can divide by the sequence or multiply by the reciprocal. So multiply by 2n factorial over pi x to the 2n power. And now I can simplify by distributing the 2 for the exponent and also the factorial. So if I rewrite it, we'll get pi x to the 2n plus 2 power over 2n plus 2 factorial times 2n factorial over pi x to the 2n power. So now I can go ahead and expand both the factorial and the exponent, so I can cancel out a couple terms. So we'll get pi x to the 2n times pi x squared times 2n factorial divided by, now if I expand 2n plus 2 factorial, it'll be 2n plus 2 times 2n plus 1 times 2n factorial times pi x to the 2n power. So now the pi x to the 2n's will cancel, and the 2n factorials will cancel. So then we're left with the limit as n approaches infinity of the absolute value. Once again, I'm going to separate the n's and the x's. So you get 1 over 2n plus 2 times 2n plus 1 times pi times x squared. So when I plug in infinity for n, notice it is bottom heavy, and 1 over infinity is basically 0. So we'll get 0 times pi x squared. And that will basically give us 0, and the absolute value of 0 is 0. And so in the ratio test, once again, we're going to set it less than 1. 0 is always going to be less than 1, so the series converges for all x. And if it converges for all x, that means our radius is going to be infinity, because it covers all x values. So now for number 3, let's find the Maclaurin series and radius of convergence of x times the inverse tangent of x. So if you know the Maclaurin series of inverse tangent of x, the shortcut of it is the series from n equals 0 to infinity. Now remember, the series, the Maclaurin series of inverse tangent of x is exactly like sine, just without the factorial. So it'll be from negative 1 to the n times x to the 2n plus 1 over 2n plus 1. So if it was sine of x, it would just have 2n plus 1 factorial, but since it's inverse tangent, we can remove that factorial. And so notice we're trying to find x times inverse tangent of x, and so x is being multiplied to inverse tangent, so we can just take the series of inverse tangent and multiply it by x. So we'll get the series from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 times x to the first over 2n plus 1. Since we do have the same bases here, we can just add the powers. So to simplify, we'll get the series from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 plus 1, or x to the 2n plus 2 over 2n plus 1. And so that is the series, or the Maclaurin series, of x times inverse tangent of x. So now in order to find the radius of convergence, we're going to use the ratio test once again. So we have the limit as n approaches infinity of the absolute value. Now once again, with the absolute value, we can remove the alternator, negative 1 to the n, and we don't need that. And we're going to replace n with n plus 1. So we have x to the 2 times n plus 1 plus 2 over 2 times n plus 1 plus 1. So we can divide by the sequence or multiply with the reciprocal. So multiply by 2n plus 1 over x to the 2n plus 2. So then when I simplify, I'll get x to the 2n, or 2 times n plus 1 plus 2, which is 2n plus 2 plus 2, so 2n plus 4, divided by 2n plus 2 plus 1, or 2n plus 3, multiplied by 2n plus 1 over x to the 2n plus 2. And so I can go ahead and expand out the exponents here. So we'll get x to the 2n times x to the 4th times 2n plus 1 over 2n plus 3 times x to the 2n times x squared. So now the x to the 2n's will cancel, and x to the 4th divided by x squared is just x squared. on the numerator, so we're left with the limit as n approaches infinity of the absolute value. Now once again, I'm going to separate the n's and the x's. So 2n plus 1 over 2n plus 3 multiplied by x to the fourth over x squared, which is just x squared. Now if I plug in infinity, notice we have the same power on the numerator and denominator. So when they have the same power, we're just going to look at the ratio of the coefficients. Since it's 2 divided by 2, the limit is 1. So we're going to get the absolute value of 1 times x squared, or simply just x squared. And we're going to set that limit less than 1, because it's the ratio test and we're trying to find the convergence interval. So now in order to get rid of the absolute value, we can set it between both the negative and positive versions of 1. So x squared has to be between negative 1 and 1. X squared can never equal a negative number, so we can just eliminate negative 1. And so remember, whenever we have x squared in an inequality, we take the square root, so x must be less than 1, and we also have to flip the sign and make it greater than the negative number as well. So x has to be less than 1 and x has to be greater than negative 1, which tells us that x has to be between negative 1 and 1. And so the radius is just the distance from the center to one of these endpoints, and the center is basically the midpoint between the endpoints, and the midpoint of negative 1 and 1 is obviously 0. So if the center is 0, then the radius is the distance from the center to one of the endpoints, and we don't have to worry about whether it's a negative 1 or 1, because the radius is always positive. So let's just pick 1. The distance between 0 and 1 is obviously 1. So that radius is equal to 1. So that is the radius of convergence along with the Maclaurin series.